In the previous video, we examined how generative AI moves from technological capability toward practical deployment. We began with the use case and looked at the different ways in which generative AI can create content, assist and automate work, support software development, analyze information, help people make decisions, and personalize communication. We then examined the two broad routes to adoption, using an existing generative AI application or integrating and customizing generative AI more deeply around organizational data, software, workflows, and business processes. From there, we examined model selection, infrastructure, data architecture, cost, security, and evaluation. We saw that successful deployment does not depend on the model alone. The use case defines the workload influences the model and workload influence the infrastructure, and the available data determine what information the application can actually use. Security, compliance, cost, and organizational requirements shape these choices further, while evaluation determines whether the resulting system performs the intended work with sufficient quality, reliability, safety, and business appropriateness. But the previous video ended with an important qualification. Even a carefully selected, well-designed, and thoroughly evaluated generative AI system continues to operate within certain limits. Generative models remain probabilistic. Their outputs can vary, they can generate statements that appear convincing but are inaccurate, and they can reproduce bias or weaknesses contained in the information on which they depend. Their performance is also influenced by prompts, retrieval systems, enterprise data, tools, applications, workflows, and the people who use and supervise them. These limitations become more important as generative AI moves from individual experimentation into organizational work. A person using an AI application to prepare an early draft can review the result before deciding whether it is useful. An enterprise application, however, may be connected with proprietary information, customer records, internal systems, business processes, or software tools. If the system is also permitted to take actions rather than merely generate information, the consequences of incorrect or inappropriate behavior can become considerably greater. This brings us to the subject of this third video, governing generative AI and designing effective human-AI collaboration. The central question is no longer simply whether generative AI can perform a task. The more important question is under what conditions its output can be relied upon, how much authority the system should receive, what controls should surround it, and where human judgment and accountability must remain. The idea of trust, therefore, requires some care. Trusting a generative AI system does not mean assuming that it is always correct, nor does it mean removing human review because the system has performed well during testing. A more useful interpretation is whether the system can be used for a particular purpose, under defined conditions, with an appropriate level of evidence, evaluation, control, monitoring, and human responsibility. The level of trust that is appropriate will therefore vary according to the task and the consequences of an error. Consider a relatively simple activity, such as brainstorming titles for a presentation, rewriting a paragraph, or generating alternative ideas. If one output is poor, the consequence is usually limited, because the user can reject it and generate another. In such cases, the AI system can be given considerable freedom to produce alternatives, while the person selects, edits, and decides what should ultimately be used. The situation changes when generative AI is used for research synthesis, business analysis, or professional recommendations. Here, the output may influence further work or contribute to a decision, so a plausible response is not sufficient. Important statements need to be grounded in appropriate evidence, sources may need to be examined, assumptions need to be questioned, and the professional using the system must determine whether the analysis is reliable enough to support the intended purpose. The requirements become stronger again when generative AI is used in healthcare, law, finance, employment, public policy, or other areas where decisions can materially affect individuals, organizations, rights, safety, or money. In these situations, the organization may require narrower system boundaries, traceable evidence, more rigorous validation, expert review, and explicit human approval before an important decision is made. The AI system may support the professional, organize evidence, identify patterns, or suggest alternatives, but responsibility for consequential judgment cannot simply be transferred to the model. There is another level of risk when an AI system can take actions. An AI agent may be able to search databases, access files, call software interfaces, change records, initiate transactions, communicate with external systems, or perform several actions in sequence in pursuit of an objective. At that point, the organization must evaluate not only whether the final answer is satisfactory, but also whether the system selected the correct tools, remained within its permissions, followed an acceptable sequence of actions, and avoided unnecessary or unsafe behavior. The question of AI autonomy therefore becomes inseparable from the consequence of error. Low consequence uses can permit relatively broad experimentation. Moderate consequence uses require stronger grounding, evaluation, and review. High consequence uses require tighter controls, evidence, specialist oversight, and explicit approval. Systems that can take actions require an additional layer of permissions, monitoring, limits, logging, approval gates, and incident response mechanisms. This gives us an important principle for thinking about generative AI in operational settings. The level of human control should generally increase as the consequence of error and the authority granted to the AI system increase. The issue is therefore not whether every use of generative AI requires the same level of supervision. It is whether the controls, evidence, and human involvement are appropriate to the risk created by the particular use case. To understand why these controls are necessary, we first need to examine the operational limits of generative AI. Hallucination is perhaps the most widely discussed limitation, but it is only one part of a wider set of constraints. Generative AI is probabilistic and non-deterministic. It can reproduce bias and noise, and it may not have access to the authoritative information required for a particular task. Its internal reasoning can also be difficult to inspect, while enterprise information may be fragmented, outdated, poorly governed, or unavailable in a form that an AI application can use effectively. There are also infrastructure and organizational limits. Generative AI requires computing resources and creates continuing inference costs. Monitoring probabilistic systems can be more difficult than monitoring conventional software because behavior may vary even when the underlying system appears unchanged. Connecting models with enterprise data and tools increases the security surface, while privacy requirements, regulatory obligations, intellectual property considerations, and contractual restrictions can impose additional boundaries on deployment. Organizations also face practical limits when moving from experimentation to scale. A successful pilot may not provide the data architecture, integration, monitoring, skills, operating model, security controls, or economic justification required for production use. Employees may need new capabilities to prompt systems effectively, verify outputs, recognize failure modes, supervise AI-supported workflows, and understand where responsibility remains with them rather than with the technology. These operational limits do not mean that generative AI is impractical. They mean that dependable use requires disciplined system design. Organizations can improve factual grounding by connecting applications with authoritative information, evaluate systems repeatedly on realistic cases, restrict access to sensitive data, limit tool permissions, monitor important actions, and continue testing after deployment. Human review can also be concentrated where the consequences of error justify greater scrutiny rather than being applied identically to every AI-supported activity. This leads naturally to governance. Generative AI governance is broader than a collection of compliance rules or restrictions on employee use. It is the organizational system through which decisions are made about what generative AI may be used for, what data it may access, which models and vendors are acceptable, how systems should be tested, who may approve deployment, what level of human review is required, and who remains accountable when the technology becomes part of a business process. Governance, therefore, includes several connected forms of control. Strategic governance establishes objectives, risk appetite, decision rights, and responsibility. Data governance determines what information may be used, who may access it, where it came from, and whether its use complies with privacy, confidentiality, consent, and other requirements. Technology and vendor governance examines models, providers, contracts, licenses, deployment architecture, connected tools, and security risks. Process controls determine how systems are tested, validated, monitored, escalated, and managed when something goes wrong. Human controls address training, AI literacy, professional review, exception handling, and accountability. Governance also includes questions of bias, ethics, reputation, intellectual property, workforce impact, transparency, documentation, traceability, and auditability. These controls must continue after deployment because models, applications, data, threats, regulations, and organizational uses continue to change. Governance should therefore be proportionate to risk rather than imposed as a single uniform structure. An employee using an approved AI application to generate alternative ideas does not require the same control regime as a system influencing a medical recommendation, employment decision, financial action, legal interpretation, or autonomous transaction. The objective is not to prevent experimentation, but to establish the conditions under which experimentation and deployment can occur responsibly. Once governance is viewed in this way, the continuing importance of the human role becomes clearer. Much of the discussion surrounding artificial intelligence is framed as a question of automation. Which tasks can machines perform, which jobs may change, and which activities can be transferred from people to AI? The examples we will examine in this video suggest that a more useful question is how work should be divided between machines and people according to their respective strengths. Generative AI can contribute speed, scale, retrieval, pattern recognition, generation, comparison, restructuring, personalization, and the ability to process large volumes of information. People contribute context, domain expertise, professional judgment, creativity, relationships, ethical reasoning, exception handling, and responsibility for consequences. The practical opportunity, therefore, lies not simply in replacing one with the other, but in designing workflows that combine these capabilities effectively. In some workflows, AI acts primarily as an assistant by preparing drafts, conducting an initial analysis, generating code, or creating alternatives for a person to review. In others, it operates as a decision support layer by retrieving and organizing evidence, identifying patterns, or proposing options, while the professional evaluates the information and makes the decision. AI may also function as a workflow guide, helping people follow required steps and capture evidence, or as a scalable first-line operator that handles routine volume while people supervise performance and take over when cases become sensitive, ambiguous, or exceptional. In creative and knowledge-intensive work, generative AI can also operate as a co-creator. The AI generates alternatives, reorganizes information, proposes structures, or produces initial versions, while the person defines the objective, supplies context, evaluates the material, redirects the process, and decides what should be retained. This changes the human role without eliminating it. Less time may be spent producing the first version, while more attention moves toward problem definition, evidence interpretation, quality control, exception handling, and final judgment. The relevant unit of analysis therefore becomes the workflow rather than the isolated task. An organization must decide what the AI will do, what people will do, where information will come from, where handoffs will occur, what evidence must accompany an AI-generated output, which decisions require approval, who will handle exceptions, and who remains accountable for the final outcome. Feedback and failures must then be used to improve the workflow as the technology and the organization evolve. In this video, we will follow that progression. We will begin by examining the principal operational limits of generative AI and how they constrain dependable use. We will then look at how those limits can be managed and why the amount of autonomy given to a system should depend on both the consequence of error and the authority granted to it. From there, we will examine generative AI governance and see how organizations can translate responsible AI principles into practical controls covering strategy, data, technology, processes, people, monitoring, and accountability. We will then turn to human oversight and examine how responsibility should be distributed as AI systems move from generating information toward influencing decisions and taking actions. Finally, we will examine real examples of human AI collaboration and identify the operating models and workflow design lessons that emerge from them. The central idea throughout the video is that the objective should not simply be maximum automation. The more useful objective is to determine where AI can contribute speed, scale, retrieval, generation, and repeatable information processing, where human expertise and judgment should remain in control, and how the two can be combined to produce a better and more accountable outcome. With that framework established, we can begin with the first question. What are the operational limits of generative AI, and why do they matter when we move from experimentation to dependable use? In the previous section, we introduced the central question of this video. Under what conditions can generative AI be trusted to operate? We also saw that the answer depends partly on the consequence of error and the amount of authority given to the system. Before we can decide what controls are appropriate, we need to understand the operational limits that make those controls necessary. An operational limit is a practical constraint affecting how reliably, consistently, safely, or economically a generative AI system can perform in a real setting. Some limits arise from the way current generative models work. Others become visible only when the technology is connected with organizational data, infrastructure, software, people, and business processes. This distinction is important because a successful demonstration does not necessarily prove that a system is ready for dependable operational use. A model may produce an impressive answer during a test and still behave inconsistently across hundreds or thousands of real interactions. An application may work technically while remaining too expensive, difficult to monitor, poorly governed, or dependent on data that are not ready for production use. The first operational limit arises from the probabilistic nature of generative AI. Conventional deterministic software is generally expected to follow defined rules and produce the same result when the same conditions are repeated. Generative AI works differently because generation involves probabilities, which means that the same or very similar inputs can produce different outputs. This variability can be useful in creative work because users may want different alternatives. It becomes more difficult when a workflow requires consistency and reproducibility. A process that depends on identical classifications, reasoning, or wording may therefore require additional constraints, validation rules, structured outputs, deterministic checks, or human review. The operational lesson is that a prompt working once does not prove that it will behave reliably in production. Testing must include repeated runs and realistic variations rather than a few successful examples. Evaluation therefore becomes part of operational readiness rather than a one-time demonstration. The second limit is hallucination, or the possibility that generative AI will produce information that sounds convincing but is inaccurate, unsupported, or invented. A language model generates likely continuations from patterns learned during training and information available within the current context. It does not automatically verify the truth of every statement before generating it. This creates an important distinction between plausibility and truth. A well-written response may appear authoritative because the language is coherent and confident, but fluency does not establish factual accuracy. The problem becomes especially important when users assume that polished language is evidence of reliable knowledge. Retrieval-augmented generation, better prompting, improved models, and authoritative information sources can reduce this risk, but they do not eliminate it. Retrieved material can itself be incomplete or incorrect, and the model can still interpret good information badly. Important factual claims therefore continue to require verification where the consequences of error are significant. The third limit concerns bias, noise, and the quality of learned patterns. Generative models learn statistical relationships from large quantities of data, and those data contain both useful information and imperfections. Biases, errors, gaps, duplication, unusual patterns, and poorly represented situations can all influence the resulting model behavior. This means that model capability cannot fully compensate for weak information. A powerful model working with poor enterprise data may still generate weak results. As generative AI becomes embedded in organizational workflows, data quality increasingly becomes part of the AI problem rather than a separate information management issue. Bias also matters because distorted patterns can produce systematically skewed or unfair outputs. The appropriate concern is therefore not simply whether an individual answer appears reasonable. Organizations must examine whether particular groups, cases, topics, or situations produce recurring failure patterns that require additional controls. The fourth limit is that information generation is not the same as information access. A general-purpose generative AI system may possess broad learned knowledge, but that does not mean it has access to every information source relevant to a particular question. Subscription databases, internal corporate records, restricted research, proprietary documents, and specialized information systems may lie completely outside its available context. This distinction is particularly important in research, due diligence, scientific review, legal work, and other evidence-intensive activities. A fluent response can create the impression that the system has considered all relevant information even when important sources were never available to it. Users therefore need to know what information the system has actually been able to access. Retrieval systems can help address this problem by connecting generative AI applications with approved external or organizational sources. But the organization must still determine which sources are authoritative, whether retrieval is complete, whether information is current, and whether the generated answer accurately reflects the evidence retrieved. A fifth limit concerns explainability and inspectability. Generative models may contain billions of parameters representing highly complex statistical relationships. Those relationships do not normally provide a simple human-readable explanation showing exactly how a particular output was produced. This does not mean that generative AI cannot support important work. It means that the level of explanation required should influence how the system is designed and where it is used. A low-consequence drafting task may tolerate limited explainability, while a consequential professional decision may require stronger evidence and traceability. In such settings, organizations may rely on source references, documented decision criteria, human review, audit trails, or complementary analytical methods. The objective is not necessarily to explain every internal model calculation. It is to ensure that important outcomes can be examined, challenged, and justified at the level required by the task. The sixth operational limit appears when generative AI encounters enterprise data. An organization may have thousands or millions of documents, records, databases, reports, messages, images, and other information assets. The existence of this information does not automatically make it usable by an AI application. Documents may be inaccessible, outdated, duplicated, poorly tagged, inconsistent, or stored across disconnected systems. Ownership may be unclear, permissions may differ, and sensitive information may require additional restrictions. A technically capable model can therefore underperform simply because the surrounding information environment is not ready. Enterprise Gen AI deployment consequently requires investment in data preparation as well as model access. Documents may need sourcing, cleaning, curation, tagging, quality control, access management, and governance. Data readiness can become one of the main constraints on moving from a promising prototype to a dependable enterprise system. The seventh limit is compute, infrastructure, energy, and cost. Generative AI depends on physical computing resources, and larger models can require substantial accelerator capacity, memory, storage, networking, and power. These requirements continue during inference every time users or applications send requests to the system. The economics can therefore change dramatically as usage increases. A pilot serving a small number of users may appear inexpensive, while an application processing millions of requests can create significant recurring costs. Token consumption, retrieval, storage, monitoring, security, integration, and human supervision all contribute to the total operating cost. This is why the most capable model is not automatically the best operational model. Smaller or specialized models may perform some narrow tasks more quickly and economically. Organizations may also route different workloads to different models rather than using the largest available model for every request. Cost therefore becomes part of system design rather than an issue considered after deployment. The relevant question is not simply what the model costs per request. It is whether the complete workflow creates enough measurable value to justify the infrastructure, integration, oversight, and continuing operating expense required to support it. An eighth limitation concerns observability. Conventional software can often be monitored through measures such as system availability, response time, error rates, and resource use. Generative AI requires these measures too, but they are not sufficient because the quality and behavior of the output can also change. Organizations may need to monitor response patterns, factual quality, safety, drift, token consumption, cost, user behavior, and recurring failure types. A system may remain technically available while the quality of its answers gradually deteriorates. Operational monitoring therefore has to include behavior as well as infrastructure. This challenge becomes greater when AI systems use tools or perform multiple actions. The final result alone may not show what happened during the process. Logs describing tool selection, retrieved information, permissions, actions, and intermediate steps become increasingly important for diagnosis and accountability. The ninth limit concerns security. A standalone conversational system that produces an incorrect paragraph creates one type of risk. A system connected with files, databases, APIs, software tools, or business processes creates a much larger attack surface because unsafe behavior may produce effects outside the conversation itself. Prompt injection illustrates the problem. A malicious or misleading instruction may attempt to push the model outside its intended behavior. If the model can only generate text, the consequences may remain limited, but if it can access sensitive information or perform actions, the same vulnerability becomes more serious. Security design must therefore develop as system authority increases. Access controls, limited permissions, isolation of sensitive functions, logging, tool validation, approval gates, and human oversight become more important when generative AI moves from generating information toward interacting with operational systems. The 10th limit arises from governance and compliance. Generative AI does not operate outside existing organizational, legal, professional, or regulatory requirements. Privacy, security, intellectual property, confidentiality, record keeping, industry standards, and emerging AI regulations may all affect how a system can be used. These requirements can also differ across jurisdictions and applications. The controls appropriate for internal brainstorming may be very different from those required for healthcare, finance, employment, or customer-facing services. Organizations therefore need to classify risks rather than assume that one governance approach will fit every application. Governance must also continue as the system evolves. Models are updated, applications change, new tools are connected, regulations develop, and users discover new ways of using the technology. Compliance and governance are therefore continuing operational constraints rather than approvals obtained once before deployment. The 11th limit concerns the move from pilot to scale. Generative AI has made experimentation relatively easy, and organizations can quickly create proofs of concept around individual use cases. But a collection of successful experiments does not automatically become a coherent enterprise capability. One risk is investing in technology without a sufficiently clear business problem. Another is allowing many separate teams to develop disconnected solutions that duplicate infrastructure, create inconsistent controls, and generate technical debt. What works as local experimentation can therefore become difficult and expensive when expanded expanded across the organization. Scaling requires an operating model as well as technology. Common infrastructure, reusable components, clear ownership, data standards, security controls, governance, and defined responsibilities become increasingly important. Organizations must also decide which components should be standardized and which should remain flexible as the technology changes. The 12th limit is human capability and workforce readiness. Generative AI may be easy to access, but effective professional use requires more than entering a prompt. People need to understand how to frame tasks, provide appropriate context, evaluate outputs, recognize weaknesses, verify important claims, and determine when the system should not be relied upon. Users also need to understand data and security responsibilities. Sensitive, personal, proprietary, or confidential information should not be entered into an AI system without knowing how that information will be handled. AI literacy therefore includes understanding limitations and appropriate use, not simply learning techniques for producing better prompts. This is why human oversight should not be viewed only as a temporary measure required until models improve. In many professional workflows, human context, domain knowledge, verification, judgment, and accountability are part of the intended operating design. The human role may change, but it does not simply disappear. The 13th limit is return on investment and use case selection. A generative AI application can work technically and still fail to create worthwhile business value. It may save too little time, require excessive supervision, create additional compliance work, or address a task that occurs too infrequently to justify the investment. Use case selection must therefore consider more than technical feasibility. Frequency of use, potential value, data readiness, error cost, infrastructure requirements, integration effort, and the amount of human checking required all affect the economics. A modest capability applied to a frequent and valuable workflow may create more benefit than an impressive system solving a marginal problem. This brings us back to the use case first principle from the previous video. The question should not be where generative AI can be inserted simply because the technology exists. The better question is whether applying it to a particular workflow creates a measurable improvement after the full operating costs and risks are considered. The 14th operational limit is the assumption that increasing model scale will automatically solve the remaining weaknesses. Larger models and greater computing resources have produced major improvements in capability, but more scale does not necessarily eliminate hallucination, bias, limited explanation, data problems, or every form of reasoning failure. This matters because model size is only one route to better performance. Better data, retrieval, tools, rules, specialized models, workflow design, evaluation, and human expertise can sometimes improve operational results more effectively than simply moving to a larger model. The appropriate system may therefore combine several approaches. A smaller model may perform one predictable task. A larger model may handle more complex reasoning. Retrieval may supply authoritative information. Deterministic software may enforce specific rules, and people may review the points where professional judgment is required. Taken together, these operational limits show why generative AI deployment cannot be treated simply as the introduction of a more powerful software tool. The system is probabilistic, data-dependent, computationally intensive, and increasingly connected with complex organizational environments. Reliability therefore depends on much more than the underlying model. The principal constraints include output variability, hallucination, bias, restricted information access, limited explainability, enterprise data readiness, infrastructure cost, monitoring difficulty, security exposure, regulatory obligations, organizational scaling, workforce capability, and uncertain return on investment. None of these necessarily prevents useful deployment, but each influences how the system should be designed and controlled. The appropriate response is therefore neither to assume that generative AI can operate without constraint, nor to reject the technology because limitations remain. The practical challenge is to decide which limits matter for a particular use case and then apply the combination of data, evaluation, controls, monitoring, and human involvement required to manage them. That leads directly to the next question. If generative AI has these operational limits, how should organizations manage them? And how much autonomy should an AI system actually be given? In the next section, we will examine how operational limits can be managed and why the appropriate level of human control should rise as the consequence of error and the authority granted to the system increase. In the previous section, we examined the main operational limits of generative AI. We saw that these include probabilistic output, hallucinations, bias, incomplete information access, limited explainability, weak enterprise data, infrastructure cost, monitoring difficulty, security exposure, governance requirements, organizational readiness, workforce capability, and uncertain return on investment. These limitations do not mean that generative AI cannot be used effectively. They mean that dependable deployment requires organizations to match the design of the system to the nature of the task and the consequences of failure. The practical objective is therefore not to eliminate every limitation, but to manage the risks that matter for a particular use case. Different limits require different responses. If hallucination or weak factual grounding is the main concern, the application may need access to authoritative information through retrieval systems. Important claims may also need verification, particularly where the output contributes to professional analysis or a consequential decision. Output variability requires a different response. Organizations can test the system repeatedly on realistic cases, use more structured prompts, define explicit output formats, and introduce rules or deterministic checks where consistency matters. Human review may remain necessary where small variations could materially affect the result. Bias and poor data require attention to the information on which the application depends. Enterprise data may need to be cleaned, curated, deduplicated, tagged, and assigned clear ownership. Evaluation should also look for recurring domain-specific failure patterns, rather than relying only on average performance. When information access is the problem, the solution is not simply to ask the model a better question. The application may need to connect with approved databases, document repositories, or retrieval systems so that relevant information is actually available. Users must also know whether an answer is grounded in authoritative material or produced mainly from the model's general knowledge. Cost requires another set of design choices. Organizations can use the smallest model that reliably meets the task requirements, route different workloads to different models, reduce unnecessary prompt and context volume, and reuse results where appropriate. The economics should be assessed across the entire workflow, rather than only through the price of the underlying model. Security becomes particularly important when models gain access to data or tools. Permissions should be limited to what the system actually needs, sensitive actions can be isolated, and tool access should be validated. Important actions may also need to be logged or subjected to an approval step before they are executed. Governance and compliance require risk classification, policies, guardrails, testing, and monitoring throughout the life cycle. Controls may also need to change as regulations, models, vendors, and organizational uses evolve. Governance therefore becomes part of operating the system rather than a separate activity conducted only before launch. Scaling introduces a different type of challenge. Organizations can reduce fragmentation by developing reusable components, common infrastructure, shared standards, and clearer ownership. This helps prevent a large number of independent pilots from creating duplicated systems, inconsistent controls, and technical debt. Workforce readiness must also be managed deliberately. Users need to know how to prompt, supervise, verify, edit, and appropriately disclose AI-supported work. They also need to understand where the AI system is useful, where it is unreliable, and where accountable human ownership must remain. These responses illustrate an important principle. The objective is not to create one universal control structure for every generative AI application. The controls should depend on the characteristics of the use case and, above all, on what could happen if the system is wrong. This leads to the question of autonomy. How much freedom should a generative AI system receive to generate information, make recommendations, use tools, or take actions without human intervention? A useful starting point is to consider two dimensions: the consequence of error and the authority granted to the system. As either increases, the need for human control generally increases as well. A low-consequence content generation task and an AI agent capable of changing a financial record therefore require very different operating models. At the lowest level are activities such as brainstorming, rewriting, formatting, and idea generation. The consequences of a poor result are normally limited because a person can inspect the output before using it. Broad experimentation is therefore usually possible, with the human selecting, editing, or rejecting what the AI produces. Consider someone using generative AI to develop alternative titles for a presentation. The AI may generate 20 suggestions, many of which may be unsuitable. This creates little operational risk because the user simply chooses the useful alternatives and ignores the rest. The same principle applies to early-stage drafting and creative exploration. Variation may even be desirable because the purpose is to expand the range of possibilities. In these cases, strict controls on every generated sentence would add friction without creating equivalent value. The situation changes at the next level, where generative AI supports research synthesis, business analysis, or internal recommendations. Here, the output may influence professional conclusions or management decisions. Source grounding, evaluation, verification, and human review therefore become more important. Imagine a consultant using generative AI to analyze a collection of market reports. The AI can summarize documents, compare findings, identify themes, and prepare an initial synthesis. But the consultant must still examine the evidence, question unsupported conclusions, resolve contradictions, and decide what should appear in the final recommendation. In this type of workflow, the AI can have substantial freedom to process and organize information, but it should not automatically become the final decision maker. The human provides context and professional judgment and remains responsible for determining whether the evidence supports the conclusion. The controls become stronger when the consequences are high. Healthcare, legal, financial, employment, public policy, and safety-critical activities can affect rights, health, money, livelihoods, or public welfare. These users therefore require narrower scope, stronger validation, traceable evidence, expert oversight, and explicit approval. A generative AI system may still provide valuable assistance in these environments. It can retrieve documents, summarize evidence, compare alternatives, identify inconsistencies, or prepare information for professional review. But assistance should not automatically be converted into decision authority. The distinction is important because an AI-generated recommendation may appear highly persuasive. In a consequential setting, however, the question is not simply whether the recommendation sounds reasonable. The organization must be able to establish what evidence supports it and who is responsible for deciding whether it should be acted upon. The highest level of operational concern arises when AI systems can take actions. An AI agent may call APIs, modify records, access sensitive files, send communications, initiate transactions, or interact with enterprise software. In these cases, the system is no longer merely producing information for a person to consider. Action-taking systems therefore require permissions that are deliberately constrained. The system should normally receive only the access needed to perform the approved task. Sensitive actions may require approval gates, while logs should allow the organization to reconstruct what the system did and why an intervention may have been necessary. Monitoring also becomes more important because the final result does not tell the entire story. An agent may eventually produce an acceptable outcome while taking an inefficient, unnecessary, or unsafe route. Organizations may therefore need visibility into the tools selected, the sequence of actions, the information accessed, and whether the system remained within its authority. Rollback and incident response can also become part of the operating design. If an AI system can change records or initiate actions, the organization needs to consider what happens when those actions are incorrect. The ability to stop, reverse, investigate, and learn from failures becomes part of dependable deployment. This gives us a practical spectrum of generative AI autonomy. At one end, AI generates alternatives and the human selects the result. In the middle, AI organizes evidence and supports professional judgment. At the higher end, AI may recommend actions under strong oversight, while agentic systems require carefully limited authority and explicit controls around consequential actions. The important point is that human involvement should not be treated as a simple yes or no choice. Different workflows can place human intervention at different points. A person may define the objective, approve the data sources, review the output, authorize a sensitive action, handle exceptions, or monitor the system after deployment. This is why the term human in the loop can sometimes be too general. What matters operationally is the exact role the person performs and where that role appears in the workflow. Human involvement is useful only when the person has sufficient information, expertise, authority, and time to exercise meaningful judgment. A review step that exists only on paper does not necessarily create effective oversight. If a person is asked to approve hundreds of AI-generated outputs without adequate evidence or time, the review can become mechanical. Good workflow design therefore requires deciding where human judgment adds genuine value rather than simply inserting approval everywhere. The same principle applies in the opposite direction. Requiring a person to approve every low-risk AI action may eliminate much of the productivity benefit that the technology was intended to create. Excessive control can therefore be inefficient, just as insufficient control can be unsafe. The objective is proportionality. Controls should be strong enough to manage the consequence of failure, but not so burdensome that they destroy the value of the system. This requires organizations to understand both the technical behavior of generative AI and the professional or business context in which it operates. A useful decision process therefore begins with the use case. What is the system expected to do, and what happens if it is wrong? What information does it need? What authority will it receive? And which actions could create meaningful consequences? The organization can then determine what evidence is required, how the system should be evaluated, what permissions are appropriate, where monitoring is necessary, and where a human must intervene. The level of oversight follows from the risk rather than from a general assumption that AI should always be either autonomous or manually controlled. This risk-based approach also helps organizations expand generative AI responsibly. A system may begin with limited authority while its behavior is evaluated in realistic conditions. Greater automation can be introduced later if the evidence shows that the workflow is reliable and the additional autonomy creates worthwhile value. Conversely, organizations may discover that retaining human involvement produces the better operating model. Full automation can sometimes create higher supervision costs, additional risk, or more complex controls than a collaborative workflow. The most advanced system is therefore not necessarily the one with the least human involvement. The underlying principle can be expressed simply. As consequence and authority increase, evidence, controls, monitoring, and accountable human judgment should increase with them. This principle takes us directly into governance. Managing individual operational limits is necessary, but organizations also need a broader system for deciding who may use generative AI, which applications are permitted, what data may be accessed, what controls are mandatory, who can approve deployment, and who remains accountable. In the next section, we will examine generative AI governance and see how organizations can turn these principles into a practical system of decision rights, data controls, technology controls, operating procedures, human oversight, monitoring, transparency, and accountability. In the previous section, we examined how organizations can manage the operational limits of generative AI and decide how much autonomy a system should receive. We saw that the appropriate level of control depends on both the consequence of error and the authority granted to the AI system. That leads naturally to governance. Once generative AI becomes part of professional work, enterprise systems, or decision processes, organizations need a structured way to decide what is permitted, what is restricted, who is responsible, and how the technology will be monitored over time. Generative AI governance can be understood as the system of processes, standards, roles, roles and controls used to direct and manage AI responsibly. It includes policies governing model development and use, data security, monitoring, safeguards, and human oversight. Governance is therefore broader than compliance alone. Compliance asks whether the organization is meeting legal, regulatory, contractual, or professional requirements. Governance asks a wider set of questions. Who may use generative AI? For what purposes? With what information? Under what conditions? And with what accountability? Generative AI creates particular governance challenges because it can be used directly by employees, embedded within software, connected with enterprise information, and increasingly allowed to use tools or take actions. The same underlying model may therefore appear in very different operational settings, each with a different level of risk. The technology also expands the range of possible failure modes. Hallucinated information, prompt injection, sensitive information disclosure, bias, intellectual property concerns, deepfakes, data provenance problems, and inappropriate tool use can all become governance issues. The organization must therefore control both the technology and the way people use it. A useful way to organize generative AI governance is through 5 broad domains. The first concerns strategic alignment and the control environment. The second concerns data and compliance. The third concerns operational and technology management. The fourth domain concerns human, ethical, and social considerations. The fifth concerns transparency, accountability, and continuous improvement. Together, these domains provide a practical structure for turning responsible AI principles into organizational controls. The first domain is strategic governance. Generative AI initiatives should be linked to business objectives, organizational strategy, and risk appetite rather than developed as isolated technology experiments. Leadership must determine which uses are appropriate and what level of risk the organization is prepared to accept. This requires clear decision rights. Organizations need to know who can approve a use case, who can authorize a model or vendor, who owns the resulting system, and who has the authority to stop or change it. Without clear ownership, responsibility can become fragmented across technology, business, legal, risk, and compliance functions. Many organizations therefore establish a cross-functional governance structure. This may include business leadership, technology, security, legal, risk, audit, finance, data, human resources, and other relevant functions. The objective is not to create bureaucracy for its own sake, but to ensure that important decisions are made with the necessary perspectives represented. A governance body also needs a clear mandate. It may define acceptable use policies, establish risk classifications, approve sensitive applications, maintain an inventory of generative AI systems, and oversee incident response. It should also be clear who has final decision authority when different functions disagree. The second governance domain concerns data and compliance. Generative AI systems can only be governed effectively if the organization knows what data they are using. This includes understanding where the information came from, who owns it, who may access it, and whether its use is permitted. Data governance therefore includes quality, lineage, access, privacy, confidentiality, consent, retention, and cross-border considerations. These controls become particularly important when generative AI is connected with proprietary records, customer information, employee data, or other sensitive material. The organization must also distinguish between information that can safely be entered into a general AI application and information that requires a more controlled environment. Employees need clear guidance because an apparently simple prompt can create a data governance problem if confidential or restricted information is included. Data quality is also a governance issue. If generative AI applications depend on retrieval augmented generation or enterprise knowledge sources, the organization needs to know whether those sources are current, authoritative, and appropriately maintained. Poorly governed data can produce unreliable AI outputs even when the model itself performs well. Compliance requirements must be considered alongside data governance. Different industries and jurisdictions may impose different obligations relating to privacy, financial services, healthcare, employment, intellectual property, consumer protection, or record keeping. The relevant controls, therefore, depend on the use case rather than on generative AI in the abstract. The third governance domain concerns technology and operational management. Organizations must decide which models, vendors, deployment environments, and connected tools are acceptable. Model capability matters, but so do licensing, contracts, data handling, security, reliability, portability, and third-party risk. Vendor assessment becomes particularly important because many organizations do not build foundation models themselves. They depend on external providers for models, APIs, hosting, or applications. Governance must therefore examine not only what the technology can do, but also the conditions under which the provider delivers it. Access control is another important element. Not every user needs access to every model, dataset, tool, or function. Permissions should reflect job responsibilities, data sensitivity, and the risk associated with the activity. The same principle applies to agentic systems. If an AI agent can access files, send communications, call APIs, modify records, or initiate transactions, those capabilities should be deliberately limited. The system should receive only the authority necessary for the approved task. Operational governance also requires standard procedures. Organizations may define how AI-generated outputs should be reviewed, when escalation is required, what evidence should be retained, and what happens when the system fails. These procedures help convert broad principles into repeatable operating behavior. Testing and validation are therefore governance controls as well as technical activities. Before deployment, the system should be evaluated against realistic tasks and relevant acceptance criteria. Sensitive systems may require more formal impact assessment, red team testing, or stakeholder approval. Monitoring must continue after deployment. Generative AI behavior can change when models, prompts, retrieval sources, data, tools, or user behavior change. Organizations therefore need mechanisms for detecting performance deterioration, unusual behavior, bias, security incidents, and other deviations. The fourth governance domain concerns people, ethics, and social impact. Generative AI governance cannot succeed through technical controls alone because employees and professionals remain part of the operating system. Users must understand what the technology can do, what it cannot do, and how they are expected to supervise it. AI literacy therefore becomes a governance requirement. Employees may need training in prompting, verification, appropriate data use, security, bias, disclosure, and the limits of automated output. Managers also need to understand where human approval remains necessary. Human oversight becomes particularly important for sensitive decisions. Organizations must determine which outputs can be used directly, which require review, and which decisions must remain with qualified professionals. A generic instruction to keep a human in the loop is not enough. The organization should specify what the human reviewer is expected to do. The person may verify evidence, interpret ambiguous information, exercise professional judgment, authorize a consequential action, or handle exceptions. Effective oversight requires both a defined responsibility and sufficient authority to challenge the AI output. Ethics and bias also require deliberate attention. Organizations may need to examine whether generative AI produces systematically unfair outcomes, mishandles privacy or consent, or creates reputational risks. The effects on employees, customers, and other stakeholders may also form part of the governance assessment. Workforce impact is particularly important because generative AI can change roles and workflows even when jobs are not fully automated. Some tasks may move to AI, while human work shifts toward review, judgment, exception handling, or higher value activity. Reskilling and transparent communication therefore become part of responsible implementation. The fifth governance domain concerns transparency, accountability, and continuous improvement. Governance requires evidence showing how important decisions were made and how the AI system was used. Without documentation and traceability, responsibility becomes difficult to establish after a failure. Organizations may therefore maintain records of approved use cases, models, data sources, evaluation results, human approvals, and significant system actions. Audit trails trails can help reconstruct what happened, particularly when generative AI is connected with operational workflows or agentic systems. Source references can also improve traceability where an AI application relies on retrieved information. If a generated recommendation depends on particular organizational documents, the reviewer may need to know which documents supported the answer. This makes the output easier to examine and challenge. Accountability must also remain explicit. The fact that an AI system contributed to an output does not remove organizational responsibility for the result. Someone must remain accountable for the system, the workflow, and the decisions made from its output. Governance also has to adapt continuously. Models are updated, new vendors appear, capabilities change, security threats evolve, and regulations develop. A policy that was adequate when a system was first approved may therefore become inadequate later. Organizations need continuing monitoring of both technology and regulation. Governance policies may need review after major model changes, new tool connections, changes in business processes, incidents, or audit findings. Feedback from users and evaluation results should also be incorporated into the governance system. This means that generative AI governance extends across the entire lifecycle. It begins when a use case is first proposed and continues through model selection, data preparation, design, validation, deployment, operation, review, and eventual retirement or replacement. At the use case stage, the organization asks whether the proposed application should be pursued. Business alignment, initial risk assessment, and risk classification help determine whether the idea is appropriate. The result should be an explicit decision rather than an informal experiment that quietly becomes operational. During model or vendor selection, the question becomes whether the technology is acceptable for the intended purpose. The organization may examine capability, security, licensing, contractual terms, data handling, and vendor risk before approval. During data preparation, the central question is whether the information is trustworthy and permitted. Data lineage, access rights, confidentiality, quality, consent, and retention become important controls. The organization should know what information the AI system is allowed to use before connecting it. During design and development, responsible controls need to be embedded into the application. These may include access restrictions, human review points, privacy controls, traceability, bias testing, and limits on system authority. Governance therefore becomes part of design rather than something added after the system has been built. Validation asks whether the system is fit for deployment. Testing results, performance evaluation, stakeholder review, and remediation of known weaknesses provide evidence for an approval decision. The required level of scrutiny should rise as the consequence of failure increases. During operation, governance shifts toward controlled use. Standard procedures, training, role-based access, monitoring, human oversight, incident response, and logs help ensure that the approved design is actually followed in practice. Later reviews ask whether the system remains fit for purpose. Changes in performance, data, models, vendors, regulations, or business requirements may require the system to be modified or reassessed. Governance therefore includes both approval and continuing challenge. Eventually, systems may also need to be retired or replaced. Data retention obligations, archived records, transition planning, and updated inventories may all be necessary. Governance continues even when an AI application is no longer being actively developed. The intensity of these controls should remain proportionate to risk. An internal brainstorming application does not require the same governance structure as a system supporting a medical, legal, financial, or employment decision, nor should a system that generates text be treated in exactly the same way as an agent capable of taking actions in enterprise systems. The objective is therefore not maximum control. Excessive governance can slow useful experimentation, while insufficient governance can expose the organization to unnecessary risk. The challenge is to create controls strong enough for the consequence of the use case without making responsible innovation unnecessarily difficult. A practical governance model can therefore be thought of as a continuing sequence. Strategy, roles, data, model and vendor, process, people, monitoring, audit, and improvement. Each element supports the next, and weaknesses in one part can undermine the effectiveness of the entire system. Governance ultimately creates the framework within which generative AI and people can work together responsibly. It defines what the AI system may do, what evidence is required, where people must intervene, and who remains accountable for the outcome. This brings us to the next part of the discussion. Governance establishes the controls, but those controls still have to be translated into actual working relationships between people and AI. In the next section, we will examine human oversight more closely and consider what meaningful human control looks like when generative AI supports professional decisions, handles routine work, or begins to take actions within organizational workflows. Around generative AI, we saw that governance establishes decision rights, data rules, technology controls, operating procedures, monitoring, and accountability throughout the life cycle of an AI system. One element appeared repeatedly across those controls: human oversight. But simply saying that a system has a human in the loop does not tell us very much. The more important question is what the person is actually expected to do. Human oversight can take several forms. A person may review an AI-generated output, verify supporting evidence, interpret an ambiguous case, approve a recommendation, authorize an action, or handle an exception. The appropriate role depends on the task and the consequences of getting it wrong. This is why organizations first need to determine which AI outputs may be used directly and which require human review. A low-risk internal draft may require only ordinary editing. A sensitive disclosure, professional recommendation, or consequential decision may require formal review before it is released or acted upon. The distinction becomes especially important because generative AI can produce confident and sophisticated language. A reviewer may be tempted to accept an answer simply because it appears polished or authoritative. Effective oversight requires the reviewer to evaluate the substance rather than the presentation. This creates what can be described as authority bias around AI output. The system may appear knowledgeable, particularly when it provides a detailed explanation or uses technical language. But confidence of expression is not evidence that the underlying information is correct. Reviewers therefore need to understand the failure modes examined earlier in this video. They should be alert to hallucinated information, bias, outdated knowledge, missing evidence, weak provenance, and conclusions that go beyond the available sources. Human review has value only when the reviewer knows what to look for. This also means that oversight requires relevant expertise. A person cannot meaningfully validate a complex legal, medical, financial, engineering, or scientific output merely by reading it. The reviewer must possess enough domain knowledge to recognize when the evidence, interpretation, or conclusion is questionable. The human role is therefore not simply to approve what the machine has produced. It is to apply capabilities that the AI system cannot reliably supply on its own. These include context, professional expertise, judgment, interpretation, and responsibility for the consequences. Consider a research or business analysis workflow. Generative AI may retrieve information, summarize documents, compare sources, identify patterns, and prepare an initial synthesis. These activities can substantially reduce the time required to process large amounts of information. The human contribution begins before the AI produces anything. Someone must define the question, determine what information matters, establish the required standard, and decide what an acceptable outcome should look like. Poorly defined objectives can lead even a capable AI system toward the wrong problem. Human involvement continues after generation. The professional examines the evidence, tests the reasoning, identifies omissions, questions assumptions, and determines whether the conclusions are justified. The AI can accelerate analysis, but responsibility for professional interpretation remains with the person. This creates a useful sequence for many knowledge work applications. The human frames the problem, the AI processes or generates material, and the human evaluates the result. The workflow combines machine scale with human judgment rather than assigning the entire activity to either one. The same principle applies to decision support. Generative AI can organize evidence, identify alternatives, summarize policies, or recommend possible actions. But presenting a recommendation is different from possessing the authority to make the decision. For consequential decisions, the human should retain decision authority and accountability. The AI may influence the decision by making information easier to understand, but the accountable professional determines what should actually happen. This distinction becomes increasingly important as AI recommendations become more sophisticated. Traceable evidence can strengthen this form of oversight. Instead of asking a reviewer to assess an unsupported AI answer, the system can provide the documents, sources, or information on which the recommendation depends. The reviewer can then examine both the conclusion and the basis for reaching it. This changes the quality of the human-AI interaction. The AI is no longer simply producing an answer that the person must either accept or reject. It is helping create a reviewable evidence package that supports professional judgment. Evidence is particularly important in regulated or high-consequence work. A reviewer may need to establish not only what the AI recommended, but why the recommendation appeared reasonable at the time. Traceability also makes later audit, correction, and investigation more practical. Human oversight also includes the ability to handle ambiguity and exceptions. Many business processes contain routine cases that follow predictable patterns and a smaller number that do not. Generative AI can often process the normal path efficiently, while unusual situations are transferred to people. Customer service provides a familiar example. An AI system may handle common questions, retrieve standard information, summarize previous interactions, and generate routine responses. A human agent becomes more important when the situation involves ambiguity, emotion, an unusual request, or a decision outside the approved operating rules. The same model can apply in professional workflows. AI handles repeatable information processing while people concentrate on cases requiring contextual interpretation. The value comes from allocating different parts of the work according to the strengths of machines and people. Escalation procedures therefore become part of human oversight. The organization needs rules defining when the AI should stop, when a reviewer should intervene, and when a matter should be transferred to a specialist or higher authority. Uncertain or disputed cases should not simply remain inside an automated process. Good escalation design also prevents the system from pretending to know what it does not know. An AI application should not be rewarded merely for always producing an answer. In some circumstances, recognizing uncertainty and transferring the case to a person is the more reliable outcome. Human oversight becomes even more important when AI systems can take actions. An agent may access files, call APIs, modify records, send communications, or initiate transactions. At that point, oversight must extend beyond reviewing generated language. Some actions may be permitted automatically within clearly defined limits. Others may require explicit authorization before the system proceeds. Sensitive actions should therefore have approval gates that place decision authority with an accountable person. The organization must also decide what the reviewer sees before giving approval. A request saying only "approve this action" provides little basis for meaningful judgment. The reviewer may need the proposed action, supporting evidence, relevant context, potential consequences, and any unusual conditions detected by the system. This illustrates a broader point. Human oversight is meaningful only when the person has enough information to exercise judgment. A human approval step can exist formally while providing very little real control. Good system design therefore considers the quality of the review, not merely its existence. The same applies to time and workload. If one person is expected to approve hundreds or thousands of AI outputs under severe time pressure, review can become mechanical. The human may begin accepting recommendations without examining them carefully. This creates a risk sometimes overlooked in automation design. Adding a human step does not automatically make a system safe. The review process itself must be designed so that human attention is concentrated where it matters. Risk classification can help achieve this. Routine, low-consequence outputs may pass through with limited intervention, while unusual or consequential cases receive more intensive review. Human attention can therefore be allocated according to risk, rather than applied uniformly to every interaction. This approach also preserves some of the productivity gains that motivate generative AI adoption. If every low-risk output requires detailed manual approval, the system may create almost as much work as it removes. Oversight should be proportionate rather than universal. Accountability is another essential element. If an organization uses a generative AI recommendation, someone must still remain responsible for the resulting decision. Responsibility cannot be transferred to the model simply because the model contributed to the analysis. This becomes especially important in professional environments. A lawyer, doctor, accountant, engineer, consultant, manager, or public official may use AI-generated information, but their professional responsibilities do not disappear. The AI becomes part of the process through which the work is performed. The same principle applies at the organizational level. Governance should establish who owns the system, who approves its use, and who is accountable when its output influences an important decision. Clear responsibility prevents failures from becoming everyone's problem and therefore nobody's responsibility. Training is therefore inseparable from human oversight. Reviewers need more than general awareness that generative AI can make mistakes. They need practical understanding of the ways those mistakes may appear in the particular workflow they supervise. Training should help people recognize unsupported claims, bias, inappropriate confidence, outdated information, and source problems. Users also need to understand the organization's approved uses, data restrictions, escalation procedures, and the circumstances in which specialist review is required. AI literacy should therefore extend beyond prompt writing. A person may be highly skilled at obtaining impressive AI outputs while remaining poorly equipped to judge whether those outputs should be trusted. Effective use requires both generation skills and evaluation skills. Organizations also need to avoid another possible problem: excessive reliance on human oversight as a substitute for good system design. A weak AI application should not be deployed simply because someone has been assigned to check everything it produces. The model, data, retrieval system, prompts, access controls, and evaluation process should first be designed to reduce predictable errors. Human expertise should then be concentrated on the areas where judgment, ambiguity, consequence, or exception handling genuinely require it. This produces a more effective division of responsibility. Technology handles the repeatable work it can perform efficiently, while people remain responsible for the parts of the workflow where context and judgment are essential. Neither side is expected to compensate unnecessarily for poor design on the other. The relationship can also change as evidence accumulates. A new system may begin with relatively strong human review, while the organization learns how it behaves in production. If performance proves dependable for certain low-risk cases, some reviews may later be reduced or redirected toward exceptions. The reverse can also happen. Production experience may reveal failure patterns that were not visible during testing. Human oversight may then need to increase, or the workflow may need to be redesigned until the problem is better controlled. Human oversight is therefore not a fixed point in the architecture. It is part of an adaptive operating model that can change as models, data, workflows, risk, and organizational experience change. This also explains why human involvement should not be regarded merely as a temporary weakness of current AI. In many professional activities, people contribute capabilities that are part of the intended system design. Context, relationships, ethical judgment, responsibility, and the handling of unusual situations remain important even when AI capability improves. The source of truth used for this video provides a practical example of that distinction. In its development, the human defined the objectives, research direction, questions, and standards, while generative AI assisted with research, synthesis, organization, drafting, and refinement. The process was iterative rather than fully automated. The human reviewed the material, questioned it, redirected the analysis, evaluated the resulting content, and retained control over interpretation and final editorial decisions. The value came from combining AI speed and synthesis with human judgment and accountability, rather than asking either participant to perform the entire process alone. That example points toward a wider conclusion. Human oversight is not only a control placed around generative AI, It can also be part of a productive operating model in which people and AI contribute different capabilities to the same workflow. Across professional applications, AI can generate, summarize, translate, compare, restructure, retrieve, and propose at considerable speed. Humans define objectives, supply context, determine what information matters, evaluate accuracy, apply professional expertise, make consequential decisions, and accept responsibility for the outcome. The question therefore begins to shift. Instead of asking only where a human must check the AI, we can ask how the entire workflow should be designed so that the strengths of both are used effectively. This takes us from human oversight into human-AI collaboration. The case studies in the source of truth show several different ways in which work can be divided between people and AI, depending on the task, the organization, and the level of consequence. In the next section, we will examine those examples and see how generative AI is being used as an assistant, a decision support layer, a workflow guide, a scalable first-line operator, and a co-creator. We will also examine what these cases tell us about the changing role of people as AI becomes part of everyday professional work. In the previous sections, we moved from the operational limits of generative AI to the controls required to manage those limits. We examined risk and autonomy, governance, and the role of human oversight when AI contributes to professional work or takes actions within organizational systems. We can now bring these ideas together. The central lesson is that governance should not be understood as a fixed collection of restrictions placed around generative AI. It is a continuing system for deciding what the technology may do, under what conditions, with what evidence, and with what accountability. An important principle is that governance should be proportionate to risk. Not every use of generative AI creates the same consequences, and therefore not every application requires the same intensity of control. Applying the strongest possible controls to every use case would make many low-risk applications unnecessarily difficult to use. Consider internal brainstorming or early-stage drafting. If the output remains inside the organization and a person reviews it before use, the potential consequence of an error may be relatively low. An approved tool, restrictions on sensitive data, employee training, and ordinary professional review may provide sufficient control. Customer-facing applications require more. An inaccurate response can damage reputation, misinform customers, reveal private information, or create other forms of harm. Grounding, testing, monitoring, approved information sources, escalation procedures, and human review for sensitive cases therefore become more important. The governance requirements increase again for financial, legal, employment, medical, and other consequential uses. Decisions in these areas may affect rights, safety, livelihoods, regulatory obligations, or significant amounts of money. Formal risk assessment, domain expert review, rigorous validation, traceability, human approval, audit, and continuous monitoring may therefore be required. Autonomous and agentic systems can require the strongest controls because they can move beyond generating information and begin to affect the external environment. An agent may call an API, alter a record, access a sensitive file, communicate externally, or initiate a transaction. Strict permissions, action limits, approval gates, logs, monitoring, rollback, and incident response may therefore become part of the system design. The principle is straightforward. Governance intensity should increase as the potential consequence of failure and the authority of the AI system increase. This allows organizations to encourage useful experimentation without treating low-risk and high-risk applications as though they were the same. Governance must also extend across the life cycle of an AI system. A use case may have been appropriate when first approved, but models, data, vendors, business processes, regulations, and user behavior can change. The question is therefore not only whether a system was fit for deployment, but whether it remains fit for purpose. Monitoring provides part of that answer. Organizations may need to watch for changes in performance, unusual behavior, bias, security events, cost, or other deviations. They also need to track relevant legal and regulatory developments and revise policies when material changes occur. Incidents and user feedback should also return to the governance process. A failure can reveal a weakness in the prompt, data, model, workflow, training, or control structure. Governance becomes more effective when these lessons are used to improve the system rather than simply recorded after the event. This creates a feedback loop between experimentation and control. Pilots can help organizations understand new capabilities before committing to broad deployment. Evaluation results, audit findings, incidents, and user experience can then refine both the technology and the governance framework. So far, our discussion has mainly concerned governance within an organization, but the source of truth also makes an important distinction between enterprise governance and the wider governance of generative AI in society. An individual organization can determine which AI systems its employees may use, what information those systems may access, how outputs should be reviewed, and who remains accountable. But some questions created by generative AI cannot be resolved by individual organizations acting alone. Issues such as copyright, labor disruption, market concentration, synthetic media, cross-border risks, privacy, and public legitimacy extend beyond the boundaries of a single enterprise. They involve governments, regulators, technology companies, civil society, researchers, professional institutions, and the wider public. This broader perspective suggests that generative AI governance also requires institutional capacity. Governments and public bodies need sufficient understanding of the technology to evaluate risks, develop policy, and oversee important applications. Governance cannot depend entirely on the organizations developing or deploying the systems. Independent assurance may also become appropriate for high-impact applications. Internal testing and audit remain important, but some systems may justify independent review or external assurance. This can provide another layer of scrutiny, where the consequences extend beyond the organization itself. Public participation is another element of the wider governance framework. Decisions about how powerful technologies affect employment, information, privacy, public services, and individual rights involve social values as well as technical performance. Dialogue among government, industry, academia, civil society, and the public can therefore contribute to legitimate governance. International cooperation also becomes relevant because generative AI does not remain neatly inside national borders. Models, data, cloud infrastructure, applications, companies, and users can operate across many jurisdictions. Shared norms and international coordination may therefore be necessary for risks that cannot be managed effectively by one country acting alone. These broader questions do not replace enterprise governance. They add another layer to it. Organizations remain responsible for their own systems, while public institutions address issues that individual companies cannot resolve independently. For an organization seeking a practical starting point, the source of truth brings the governance discussion together into a relatively simple control architecture. The first step is to establish the organization's generative AI objectives, principles, and appetite for risk. The second step is to create clear governance authority. A cross-functional body may bring together business, technology, data, security, legal, risk, compliance, audit, human resources, and other relevant expertise. What matters is that decision rights and accountability are explicit. The organization should then know where generative AI is actually being used. This requires an inventory covering approved systems, experiments, embedded AI features, and applications already in production. Governance becomes difficult when the organization does not know which AI capabilities are operating inside its own environment. Each use case can then be classified according to risk. A drafting assistant, customer support system, professional decision support application, and autonomous agent should not automatically follow the same approval path. Classification allows controls to be matched to consequence. Data then becomes a central governance layer. Organizations need to manage what information enters generative AI systems, where it came from, whether its use is permitted, who may access it, and how confidentiality and retention are handled. Trustworthy AI depends partly on trustworthy and properly governed information. Models, vendors, contracts, embedded AI features, and connected systems must also be assessed. Choosing a model is not simply a question of capability. Security, confidentiality, licensing, vendor risk, deployment architecture, and the systems to which the AI will be connected can all determine whether a technology is suitable. The next layer is the operating process. Organizations need rules describing where generative AI may be used, how applications are tested, what standards they must meet, what outputs require review, and when escalation is necessary. Broad principles become useful only when they are translated into operating procedures. People form another essential part of the control architecture. Employees need to understand both the capabilities and the limitations of the systems they use. Training should include data responsibilities, bias, intellectual property, verification, approved use, escalation, and the circumstances in which human judgment must remain decisive. Monitoring then provides evidence about what happens after deployment. Performance, security, compliance, incidents, model behavior, and changing use patterns may all require attention. A system that passed evaluation at launch cannot simply be assumed to remain appropriate indefinitely. Documentation, logs, traceability, and audit evidence provide the final supporting layer. Organizations should be able to reconstruct important decisions and understand how consequential outcomes were produced. This becomes especially important when AI systems interact with data, tools, or operational processes. The governance process therefore becomes a cycle rather than a checklist. Strategy establishes direction, roles establish responsibility, data provides the information foundation, models and vendors provide technological capability, processes determine how that capability is used. People provide expertise, judgment, and oversight. Monitoring reveals what happens in practice, while audit and feedback identify where the system needs to improve. A useful way to represent the sequence is strategy to roles, to data, to model and vendor, to process, to people, to monitoring, to audit, to improvement. The sequence also shows why governance cannot belong only to the technology department. Decisions about generative AI increasingly touch business strategy, information management, professional responsibility, cybersecurity, risk, regulation, workforce capability, and organizational change. This brings us back to the question with which this video began. Under what conditions can generative AI be trusted to operate? The answer is not that the model must become infallible. Current generative AI remains probabilistic, can hallucinate, can reflect bias, can operate with incomplete information, and can behave differently as models, prompts, data, and tools change. Trust therefore comes from the quality of the surrounding system. The organization chooses an appropriate use case, supplies reliable information, selects suitable technology, evaluates performance, limits authority, applies proportionate controls, monitors behavior, and retains human judgment where the consequences demand it. The objective is neither unrestricted automation nor rejection of generative AI. It is disciplined deployment. The organization should know what the AI system is expected to do, what it is permitted to do, how its performance will be evaluated, and what happens when it reaches the limits of its competence or authority. Human responsibility remains central to that design. As we saw in the previous section, oversight is meaningful only when people have the expertise, information, authority, and time required to exercise judgment. Simply inserting a nominal human approval step does not create responsible use. This leads to an important conclusion from the governance discussion. The challenge is not only to control generative AI, it is to determine how people and AI should work together once the technology becomes part of a real professional workflow. Generative AI can contribute speed, scale, retrieval, pattern recognition, generation, comparison, and routine information processing. Humans contribute context, domain expertise, professional judgment, creativity, relationships, ethical reasoning, exception handling, approval, and accountability. The most useful operating model may therefore not be one in which the human performs everything, nor one in which the AI performs everything. The opportunity lies in allocating work according to the comparative strengths of each. That shifts our attention from the AI model to the workflow. Which tasks should be assigned to AI? Which should remain human? Where should the handoffs occur? What evidence should accompany an AI-generated output, and who should approve consequential decisions? These questions take us beyond governance and into the design of human-AI collaboration. In the next video, video 5, we will examine this subject through practical case studies from different industries and professional settings. We will see how organizations are using AI as an assistant, a decision support layer, a workflow guide, a scalable first-line operator, and a co-creator. We will also examine how these arrangements change jobs and professional workflows. The question will not simply be whether AI replaces people, it will be how tasks are redistributed, how human expertise changes, and how organizations can preserve judgment and accountability while gaining the speed and scale that AI can provide. Finally, we will develop a practical framework for designing human-AI workflows. We will examine where AI should act, where people should intervene, how handoffs should work, what should be measured, and how feedback can improve the system over time. The central idea we carry forward is therefore this: responsible generative AI does not end with selecting the right model or putting governance controls around it. Its real value emerges when technological capability, organizational controls, and human expertise are combined into a workflow that produces better, more reliable, and more accountable outcomes. That is the subject we will take up in video 5, Human-AI Collaboration.